Hey everyone, welcome back. Today we're taking a deep dive into something that's both a headache and a goldmine.
Oh, yeah.
Massive spatial data sets.
Okay.
Think about the sheer volume of information gathered by satellites and aircraft constantly scanning the Earth.
Right.
It's like trying to drink from a fire hose.
It really is a data deluge.
Yeah.
And traditional methods for analyzing this kind of information just aren't designed to handle that scale.
So what happens when we try to crunch all this data using the old school methods?
Well, imagine you're trying to solve a giant jigsaw puzzle.
Okay.
But instead of putting the pieces together bit by bit,
Right.
you're trying to analyze the entire puzzle at once.
Yeah.
It's overwhelming, to say the least.
Okay, I see the problem. Too much data, not enough processing power.
Yeah.
But that's where this intriguing concept called multi-resolution approximation, or MRA, comes in, right?
Exactly.
Our deep dive today is based on a fascinating research article all about it.
Exactly. MRA takes a different approach.
Right.
Instead of treating all data points equally,
Right.
it uses a clever hierarchy, kind of like that jigsaw puzzle analogy.
I like it.
You start by dividing the data into smaller, more manageable chunks or regions.
So instead of choking on the whole puzzle, we break it down into smaller sections we can actually handle.
And then within each section, we strategically choose a few key points,
Okay.
kind of like representative samples
Got it.
called knots.
So it's like choosing delegates from each region to speak for the whole group.
That's a great way to put it. At the most detailed level, we can still use traditional methods within these smaller regions
Okay.
because we have fewer data points to process.
Right.
Then, as we zoom out to larger regions,
Yeah.
we essentially summarize the information from those finer levels, capturing those bigger patterns.
Ah, so we're working our way up the ladder, from the small pieces to the big picture.
Precisely.
Just like assembling a jigsaw puzzle.
And this hierarchical approach has some major advantages.
Okay, like what?
First off, speed.
MRA is significantly faster than trying to force traditional methods on these massive data sets.
That makes sense.
Yeah.
Breaking it down makes the task much more manageable.
Right.
But what about accuracy?
Well, that's the surprising part. MRA can be incredibly accurate,
Really?
often even better than some other shortcut approaches.
Wow.
Plus, it's perfect for modern computing environments where we can distribute the work across many machines.
So we're talking faster, more accurate, and scalable.
Exactly.
Okay, I'm officially intrigued, but I have to ask, what's going on under the hood? How does MRA actually pull off this magic trick? The article mentions these things called basis functions.
Right.
What are those all about?
Think of basis functions as the building blocks of MRA.
Okay,
They're simple shapes that can be combined to represent complex patterns in the data.
so like Lego bricks that you can assemble into all sorts of structures.
Exactly. And here's where it gets really clever. MRA automatically figures out the best combination of these basis functions to match the specific data we're analyzing.
That's impressive. So no more manual fiddling. MRA does the heavy lifting for us.
Right.
Now, I'm really curious to see this thing in action.
Okay.
Do we have a real-world example of MRA at work?
We do. The researchers put MRA to the test using a massive data set of satellite measurements of total precipitable water, or TPW.
TPW, that sounds pretty technical.
It's essentially a measure of how much water vapor is in the atmosphere above a specific point.
Okay, so it's all about tracking atmospheric moisture.
Right.
Why is that data so important?
Well, this information is crucial for weather forecasting and understanding precipitation patterns.
Okay.
And in this case, the data set they used was enormous, over 270,000 measurements.
Wow, that's a lot of water vapor to keep track of. So how did MRA handle this massive data set? What were the researchers comparing it against?
They compared MRA to two other methods.
Okay.
A simpler one that treated different regions completely independently.
Got it.
And a slightly more sophisticated approach, kind of like a less advanced version of MRA.
Okay, so it's MRA versus two contenders in a data crunching showdown. And the winner is...
As you might expect, MRA was blazingly fast.
Okay.
But what's really impressive is that it actually produced more accurate predictions than the other methods,
Wow.
especially when dealing with large areas where data was missing.
Hold on, so not only is it faster, but it's also better at filling in the gaps.
Exactly.
That's amazing. What about those other methods? Any major weaknesses we should know about?
Well, the simpler methods created these noticeable blocky artifacts in the predictions. You could literally see the artificial boundaries where they were trying to piece together the data.
So it's like the difference between a smoothly blended painting and one where you can see the individual brush strokes. Not very elegant.
MRA, on the other hand, created much smoother and more realistic transitions.
This is all incredibly fascinating, but I think we need to pause here for a moment and let our listeners process all this amazing information.
Okay. We'll be right back with more insights on MRA and its potential.
Sounds good. Yeah, it was really interesting how MRA was able to just smoothly blend that data together.
Right.
It captured those continuous transitions
Yeah.
that the other methods just couldn't handle.
And as you mentioned before,
Yeah.
accurate long-range predictions are especially crucial when we're dealing with satellite data
Right.
because there are always going to be gaps
Yeah,
in what the satellites can see.
exactly. Like cloud cover, for example.
Oh, right.
Satellites can't see through those thick clouds,
Mm-hmm.
which means there are going to be holes in the data for those regions.
Yeah.
And MRA is really good at filling in those gaps, realistically.
So in this analysis of water vapor,
Yeah.
MRA is faster,
Yes.
more accurate, especially with missing data,
Right.
and it avoids those blocky artifacts.
Exactly.
Anything else we should know about how it performed?
Well, the researchers also used some pretty sophisticated statistical measures.
To confirm the accuracy of MRA's predictions.
So beyond just eyeballing the results,
Right.
they had some hard numbers
Yeah.
to back up those claims.
Exactly.
That's reassuring. But were there any downsides to using MRA compared to those simpler methods?
Interestingly, all three methods ended up with pretty similar processing times.
Oh, really?
But this particular analysis.
So it's not that MRA is inherently slower.
Right.
It's more like it was able to achieve better results
Yeah.
with a similar amount of computational effort.
Exactly. And it's worth noting
Yeah.
that all three methods produced those slight artifacts
Okay.
in areas where the data was very certain.
Right. That slightly blocky appearance in those regions of the prediction maps.
Yeah.
So it seems there's still room for improvement even with MRA.
Absolutely. There's always room for improvement and refinement with any statistical method.
Of course.
But overall, MRA clearly demonstrated its strength in handling massive spatial datasets, particularly when it comes to making those long-range predictions and filling in data gaps.
Okay. I think I've got a good grasp on how MRA works and its advantages.
Okay.
But before we wrap things up, I want to zoom out a bit.
Okay.
Why should our listener care about all this? What's the big takeaway?
That's a great question. Remember, we're talking about analyzing data.
Right.
That helps us understand our planet in some pretty profound ways.
Yeah.
This water vapor analysis is just one example.
Of course.
MRA can be applied to all sorts of other spatial data sets,
Like what?
like those related to climate change,
Okay.
pollution monitoring, or even resource management.
So the implications go way beyond just weather forecasting.
Right.
This is about gaining a deeper understanding of complex systems that affect all of us.
Precisely. And if we can analyze these massive amounts of data about our planet accurately and efficiently,
Yeah.
it opens up a whole new world of possibilities.
Oh.
We can make better predictions about future trends, manage resources more effectively, and ultimately make more informed decisions.
No, that's a powerful thought. It makes me wonder what other groundbreaking applications of MRA might be just around the corner. I mean, we've talked about weather and climate, but could this type of analysis be used for other things completely?
It absolutely could. For example, imagine applying MRA to something like social networks.
Okay.
These networks generate huge amounts of data
Right.
about how people interact and share information.
Wow, yeah. Could MRA help us understand how ideas spread or even predict social trends?
It certainly has the potential.
Wow.
And then there's the world of finance.
Okay.
Financial markets generate mountains of data every single day.
Yeah.
Could MRA help us make sense of it all?
Yeah.
Maybe even predict market fluctuations.
Okay, now my mind is really racing. From weather patterns to social trends to the stock market, it seems like the possibilities are endless. But before we get completely carried away, I think we need to take a moment to gather our thoughts. We'll be right back with some final reflections on this incredible tool and its potential impact.
Sounds good.
Welcome back, everyone. We've been on quite a journey.
Yeah, it really has.
Exploring this powerful tool called MRA,
Right?
from tackling massive data sets of weather patterns to potentially decoding social trends
Yeah.
and financial markets.
It's really amazing.
It seems like we've only just scratched the surface of what MRA can do.
It's true. The potential applications are incredibly vast.
Yeah.
And as computing power continues to grow,
Right.
those possibilities will only expand further.
So as we wrap up this deep dive,
Okay.
what's the one key takeaway you want our listeners to walk away with? What's the big so what of all this?
Well, I think the biggest takeaway is that we're living in an age where we can extract meaningful insights from data
Hmm.
on a scale that was previously unimaginable.
Yeah.
Whether we're talking about understanding our planet,
Hmm.
predicting social trends, or navigating the complexities of financial markets,
Yeah.
MRA offers a way to make sense of it all.
It's almost like having a new lens
Yeah.
through which to view the world.
Exactly.
One that allows us to see patterns and connections that were hidden before.
And with that newfound understanding
Yeah.
comes the potential to make better decisions,
Like,
whether those decisions are about climate policy,
okay.
resource management,
Mm.
or even personal investments.
It's exciting and empowering,
Yeah.
but it also feels like a big responsibility. With
Right.
all this data at our fingertips,
Right.
we need to be thoughtful about how we use it.
Absolutely.
Yeah.
Data is a powerful tool.
Yeah.
And like any tool, it can be used for good or for ill. That's why it's so important to think critically about the ethical implications of data analysis
Okay.
to ensure that we're using these insights to create a more just and sustainable world.
Well said. On that note of responsible innovation,
Yeah.
I think it's time to wrap up our deep dive into the fascinating world of MRA.
It's been a pleasure exploring this topic with you.
And to our listeners,
Yes.
thank you for joining us on this journey of discovery. We hope you've gained a new appreciation for the power of data and the innovative ways we can use it to understand our world and shape our future. Until next time, keep exploring.